and some and how to work with the basics, single gate with NOT, then single gate with Hadamard, single gate Hadamard with C0. So means what? So superposition and your entanglement, circuit composing, how to compose a circuit, and the QASIM, and how to obtain the result from running from your hardware QC anywhere in the world. Then what all the resources, up-to-date resources available for QC, blogs, and reputed textbooks towards QC. And that's it. That is the thing I'm going to cover.
Wonderful. So as you've heard, you've got a busy day ahead of you today. And then I know you have a few more busy days ahead of you for the rest of this week. Again, I'm thrilled to get to be one of the first people to talk with you all and start you on this journey. I want to start with just some very basic overall thoughts for everyone. So let me see some hands over there. Give me a thumbs up if you could see my screen. Nice. Those are great hands up in the air. I love that. What I want to start with is the congratulations on being here in the first place. Out of all of the people who applied, only you were the people that were chosen to be a part of this workshop series. The organizers that put this together for you, they see great potential in you. And that is a huge thing to start with. You should be really proud that you are sitting in the seats that you are, behind the screens that you're sitting at, getting to be here. I also want to let you know that failure is an option. And in fact, it is recommended. When you begin your journey into quantum computing, you're going to hit a lot of roadblocks because, number one, it's a difficult field to understand if you have no background in it. But number two, there's just so much in the field that it can be very overwhelming to figure out which direction for you to even start in. So don't worry if you hit some failures along the way. You should not hope to understand everything that we say over the next 5 days right away. This will take time to sink in, and it will take time for you to understand what maybe something you hear tomorrow really means in the big picture. This is on purpose, right? We're doing this on purpose. We have these 5 days to jam pack as many things in as possible, but we do not expect you to be quantum computing experts at the end of just 5 days. This should really be a kick-started way to get you to where you eventually will be. I also want to encourage you to see other learning resources. And I'll give you an example. I just recently tried learning about a quantum computing concept called the CHSH game. I tried 3 different ways. I tried learning about it from a textbook, like an actual textbook in my hands. I tried reading an online textbook, and then I tried talking to a professor about it. And none of that made it click in my head. There was some part of it missing. This was, failure for me, right? Don't be afraid of failure. And finally, what I did to make it, click in my head was I watched a YouTube video and I talked to one of my friends in the field. And I had that friend watch the video with me and I asked them questions as it was playing. And that's finally what made me understand this concept in a really strong way. I encourage all of you to find whatever method works for you. If listening to me talk today does not work for you, that's okay. I won't take it personally, and you should not feel like that's a big deal either, right? Everyone has their own best way of learning, and part of this 5-day workshop series is about you figuring out what your best way of learning is. Finally, I want to just say that you should take advantage of this opportunity in every way. Network both with the people you're sitting around, but also with the speakers that you see. make new friends to help you along your journey of learning. Working with other people is always really helpful for me, and it might be for you too. Work your butt off, right? This is going to be a lot over these next 5 days, but really dive into it. Be an active learner. Try to do as many of the things as you can. And finally, ask questions when you have them. During these 5 days, not only will you have access to folks from industry or grad students or people that have PhDs in quantum computing, but you're also going to be sitting around other people that are learning about it who could answer those same questions. So ask those questions, because now is the best time to get them answered. And I say all that just to remind you that we really believe anybody can learn quantum. Truly. I don't think everybody in the world needs to be a quantum expert. Everybody in the world does not need to have a PhD, but no matter who you are, whether you're a grandmother or whether you're sitting, in a high school classroom or anywhere in between, anybody can learn some part of quantum, and it will be good for you in the long run. So you've already seen your schedule for the next 5 days, right? And you know that we have multiple speakers each day. We've got some lectures. On some of the days, you'll have lab sessions and Q&As and quizzes and different things like that. Throughout all of this, there is going to be lots of repetition. Speakers will be talking about the same concepts, and you might hear the same thing explained 2 or 3 different times. Again, that is on purpose. We know that if you only hear something once, the chance that you fully understand it and can apply it to a future idea, it's not that strong. So the speakers are going to be repeating a lot of the same things that we've talked about in previous days to make sure that the understanding is there. So I hope that helps set your expectations for the next 5 days of what you should be doing and what you can expect to get out of all of this. And so with that, I'll begin kind of my part of everything. But before I do, are there any just questions here at the start? Okay. I'll dive in. All right, I want to start with a story about the game of chess. Now, this is an old fable. I'm not sure exactly how true the story is or not, but the idea was that thousands of years ago, the person who invented the game of chess brought it to the emperor of their area and said, "I made this game for you, emperor. I'm so proud of this new game of chess." So the person taught the emperor how to play, and the emperor loved the game and said, "You know what? I love this game so much, I will give you any reward you would like for this game, for sharing this game with us." So the inventor thought for a little bit and then said, "You know what I would like? I would like 1 grain of rice for each square on the chessboard, but every day. So give me 1 grain of rice on the first day, and the next day, all I want you to do is just double the amount of grains of rice." Now, there's only 64 squares on a chessboard, right? 8 by 8. So the emperor, thinking to themselves, "Oh my goodness, that's easy. I'll do that." Said, "Yes, I will gladly give you 1 grain of rice doubled each day for each square on the chessboard." Well, after 1 day, the inventor had a single grain of rice, not very much. After a week, the inventor had 127 grains of rice. Again, not very much. The emperor was kind of chuckling, thinking, "Oh, I got away with something here." But suddenly, that starts to change. After 30 days, this was 268,000 bags of rice. Now the inventor is looking around saying, "I'm pretty good." And the emperor is thinking, "What did I get myself into?" Because after the full 64 days, that was 461 billion metric tons of rice. Clearly, sometimes these things can get a little out of hand. My name is Brian Ingmanson. I'm here from IBM Quantum, and I am here to talk to you about quantum computing and how to start your journey down that path. This story that I talked about just reinforces the idea that anybody can learn quantum, because that story of Rice is the story of quantum computing, believe it or not. I know it doesn't sound like it, but I'll explain it in just a few minutes. See, the scale of quantum computing, that's the thing that is the most interesting. And that's where I like to start always talking about it. I'll give you another example. How many ways could I arrange a dinner party of just 10 people? I've got one table. I've got 10 people sitting at that table. Think to yourselves and raise your hand if you think you know the answer. I'm not going to ask you to shout it out, but just raise your hand if you think you know it. All right, I don't see many hands raised. That's okay. That means we're starting at the right place. The answer is 10 factorial, which means 10 times 9 times 8 times 7, all the way down to 1. And when you actually do that multiplication out, that ends up being over 3.6 million different ways that you can see just 10 people around one single table. I know that seems like that must not be true, or that like I must be lying. That can't be it. But when you actually look at, okay, if person A sits here and then you shift everyone around, person A sits there and you shift everyone around, the amount of answers quickly grows out of what you might expect. And it just illustrates that some problems are bigger than you might think. So you might be thinking, don't we already have really powerful computers that can easily handle these big problems? In fact, some of you probably have smartphones that you could do that exact problem on right now. And the answer is yes, of course we do. The IBM Summit supercomputer is a great example of that, right? IBM and many other companies have built very powerful computers that can do really strong calculations. However, even with 250 million gigabytes of storage, that's not enough to perfectly model something that many of you eat or consume every single day, which is caffeine, a caffeine molecule in your tea, in your coffee, in your Red Bull, if you have any of that, right? No, caffeine is all around the world. But caffeine is something that our strongest supercomputers cannot perfectly model. See, really small things like molecules, they behave differently than what you might expect. The different forces from the electrons, the chemical bonds, and the other atomic interactions are overwhelming to perfectly simulate. And if we use a classical computer, it would be impossible, like I said, impossible to perfectly model all of the atoms within a single caffeine molecule. There's just too many different interactions at the quantum scale. And I'm using that word perfectly on purpose, right? We can definitely model a caffeine molecule to our best approximation. We can model it, in theory, but to perfectly model it, that is still too much for our computers to do. So some problems are too small for us to see clearly, even with the computers we have today. And yet, caffeine exists, right? Nature has figured out what a caffeine molecule should look like perfectly. Our computers cannot figure it out, but nature knows that a caffeine molecule should exist, right? I'm drinking coffee right here in this. It's helping me get through this nice early morning. And this idea that nature has solved things that our computers cannot, that's really interesting. And it's not just true for caffeine, right? It's true for pretty much every organic molecule in the world. Nature has understood what that molecule should look like, how a protein should fold inside your body. It's understood all of these things for millions of years, even though we only invented computers, less than a century ago. This idea of big and small is exactly where quantum computing lives. Classical computers, like the ones you're sitting in front of, they follow the classical laws of physics. But quantum computers follow the laws of quantum mechanics, which are the laws of nature, which explain how things behave on that really small scale. Our scientists have harnessed this to our advantage, and quantum computers can tackle really big problems much more efficiently than how a classical computer might. And quantum computers use some special properties of quantum mechanics to be able to do that. So I'm going to pause for a sec before I go any further. Again, show of hands. I'm looking at all your hands right now. How is this feeling? Raise your hand if, yes, I followed that, Brian. I understand where we are. Or keep your hand down if I'm still pretty confused. Great. Okay, perfect. Love to see that. All right, so let's move forward. So we harness the laws of nature to tackle hard problems. That's what a quantum computer is doing. So let's talk about the thing that makes it all happen, a qubit, and why it's so special. Inside of our quantum computers, we have a quantum bit of data, or a qubit. That's where the name comes from. And qubits have special properties that a normal computer does not get to have. Now, just so you know, there are a few different ways to physically make a qubit. It's kind of like a bridge. There's different types of bridges in the world, and they're constructed in different ways, but they all serve the same purpose. Qubits are very similar. The technology that IBM uses is different than the technology that D-Wave uses or some other companies. However, we're all trying to do the same thing, regardless of how we build them. So let's talk about this through superposition. I'm going to bring up a piano here. Can you see the piano? Raise your hand if you can see the piano. Okay, cool. And now let's see if you can hear the piano. Can you hear it? Yes. Okay. Okay, beautiful. So with a classical computer, every piece of information is like a single note on a piano. It's either on or it's off. When it's off, you cannot hear it. When it's on, you hear it. And there's no in between. With a quantum computer, we are able to do something called superposition, which is to take a series of qubits and put them into something called a superposition where there's an equal probability that they're on or off. There we go. There we go. So with a quantum computer, we give each of these notes a probability that they will or will not be played. And we can put multiple qubits or multiple notes next to each other. And we can even have them interact with each other. We could tell one note, I only want you to play if this one plays. And then we could say, I only want this one to play if this one plays. And now suddenly, we've built this beautiful chord all together with our qubits. That is, in essence, what superposition is. We're taking one piece of data and we're giving it a chance to be something more than just a 0 or a 1. Now, I am very simplifying this idea of superposition. There are lots of intricate mathematical equations that you will see maybe later today, maybe tomorrow, that explain what is actually happening in superposition. And there's even further complicated mathematical equations that show you how powerful it is to use superposition. So please know that me talking about a piano is just a way for you to understand the basics of what superposition is. It's just this idea that a qubit has more probabilities within it than just 0 or 1. There's a chance it can be more than that. And we use that to our advantage, right? A classical computer uses a single note. Quantum computer can use chords, and it can contain a combination of different possible states or notes called superposition. Here's the trick, though. When you actually listen to that chord, you can only hear one of the notes within it. Nature didn't want to make it too easy for us to hear its secrets. So even if I have this beautiful chord on a quantum computer, when I actually look at what's happening, I might only see one of those notes. Now that's tricky, right? That's not quite fair. And that's one of the things that makes quantum computing so difficult to understand in the first place, and so difficult to harness to make real progress. This idea that superpositions have all this glorious potential, but when you actually look at it, when you measure what's happening, it flattens everything out to just one thing. That makes it really difficult for us, but it's also a really fun problem to have. So I want you to keep that in mind too, that, you know, this idea that even though there's this glorious chord, at the end of the day, when you're measuring it, you see very little data about what happened within that chord. That's something fun. Now let's talk about another part of a quantum bit of data, of a qubit. This is called entanglement. So this is another special thing on top of superposition. Quantum computers allow us to take two different qubits and do something unique with them. It is hard to describe because we don't have a real world counterpart to this, but essentially, when we entangle qubits together, we connect them in a really unique way. And when we observe just one of the entangled qubits, we can instantly learn something about the other qubit, even without looking at it. It's kind of like if I took two pieces of paper, if I wrote the number 0 or 1 on that paper, and then I took another piece of paper and wrote 0 or 1, and I crumpled them both up into balls and threw them to two different directions. If one of you walked that way and picked up the piece of paper over there, and you saw that I wrote a 0 on it, you would know right away that the piece of paper over there also has a 0. Now, again, I am simplifying this idea of entanglement down just so we can understand what's going on. But this combination of superposition and entanglement gives us a new tool set of things that we can do with quantum computers that we could not do with classical computers. So quantum computers use special bits of data called qubits. They follow the laws of quantum mechanics. We use these laws to our advantage, enabling us to put qubits into superposition or to create entanglement. And using these techniques, we harness nature to compute problems that are too large for classical computers to solve. That's where we're at with quantum computers. So now I want to show you a little bit about what a quantum computer looks like. This is an IBM quantum computer. This is a new one that was just unveiled in Cleveland, Ohio, in the United States. And this quantum computer is called the IBM Quantum System 1. Now, the computer is inside of that big silver cylinder there in the middle. And I'll explain the different parts of what's going on here. See, inside that cylinder, there's this chandelier. That's what we call it. And this chandelier is full of cables that are sending information up and down to our qubits and also maintaining the environment within that chandelier. Here's what one actually looks like. I know it's a little blurry, but way at the bottom of that chandelier is the actual quantum processing chip itself. And it's about the size of a stamp. So everything that happens on a quantum computer, that's what we're talking about. This little thing the size of a stamp, that's where all of the calculations are actually happening. And everything else that you see in a quantum computer, all of those coils, those cords, those big chandeliers, all of that stuff is there to maintain the environment and make sure our qubits are working the right way. It's pretty fascinating to see one up close and in person. They make these space age noises. There's gold plating all over them. There's copper wires. This is my buddy Nick right here working on one of those quantum computers. So there's a lot of really interesting stuff happening within them. But that chip, right, that stamp-sized chip, when you zoom in on it, you can see the different parts of the quantum computer. These dark blue squares, those are the qubits, or yeah, our qubits. Forget I said quantum pennies. I got to delete that part. The squiggly lines, those are microwave resonators, which is how our pennies talk to each other. The computer sends information through those as well. And to work properly, all of this needs to be colder than outer space. We keep it at 0.015 Kelvin. So this is an extremely cold situation for our qubits to actually work properly. Here's how it all happens. On your laptop or on the computer in front of you, you send some instructions to a real quantum computer. Those instructions get analyzed by our computers and turned into microwave pulses. Those microwave pulses travel all the way down to the qubits themselves, and they talk to the qubits. And then the qubits respond with their own microwave pulses. Our computers then translate those back to zeros or ones, and then send that 0 and 1 back to you in front of your computer. That's the whole process that you will be doing pretty shortly. So I want to now talk about what quantum computers are used for, just some of the use cases, but I want to pause and see if there's any questions. All right, I see no hands up, so we will go on.
There's a hand up here.
Oh, I'm sorry, go ahead. I didn't see it.
Brian,
Yes.
you likened quantum mechanics to the laws of nature as compared to that of the classical types. I'm a bit confused. Can you clarify that part a bit for me? Because we know that usually the classical types.
Yeah, absolutely. So the best way to think about this, let me go over, I'll go back to this slide. The best way to think about this is that quantum mechanics and quantum computers, like I said, they behave how things act on a very small scale. So the way electrons act, for example, the way they behave is different than how this pen in my hand behaves. Things that we can interact with, like as humans, because we are so big, because we're so massive, we follow, again, classical physics. Things like gravity, you know, that is something that we have to worry about all the time. But electrons are so small that they don't have to worry about gravity, right? Electrons spin around an atom and they spin wherever they want to spin. Gravity is not pulling electrons down to the bottom of an atom and keeping them there, right? Those electrons are spinning all around. So that's a really good example of what I mean by that really small stuff, those quantum mechanical things, they act differently. So when I say we harness the laws of nature, what I really mean is we're harnessing how nature works on that really small scale. Things like electron movements, things like superposition. That is the type of stuff that nature does already, but it's things that we humans do not do. So nature has been spinning electrons, you know, since the dawn of time. For 4.3 billion years, electrons have not worried about gravity. But we humans just learned about this recently. So again, when I say we're harnessing the laws of nature, I really mean we're harnessing the really small, weird laws of nature. Does that help explain that?
Yes, please.
Okay, awesome. Thank you so much for the question. Okay, so going back to now, what are quantum computers?
Hello.
Oh, yes.
We have
Yes.
a question.
Oh, I'm so sorry. Go ahead.
Quantum computers said they give back the microwaves to zeros and ones, but you also said they work in the probability, so zeros, ones, all mixed together. So why do they have to like now come back to zeros and ones?
Great question. Really good question. When a quantum computer is working, right, when the qubits are in superposition, when they're entangled, they are not just a 0 or a 1. They are a really complicated combination of those probabilities, like you just said. That's a perfect word for it, that combination of probabilities. When they send information back to us, we call that measuring the qubit. And what we're doing is we're saying to the qubit, okay, I need to learn some information from you right now. This is what I was talking about with the piano, right? The really tricky thing is when we measure what's actually going on, all of that beautiful superposition, all of that combination of probabilities gets flattened into just a 0 or a 1. And that's all we can learn from it at this time. Now, we're hoping maybe in the future that scientists can come up with a way to better analyze what's happening within a superposition without fully flattening it. But right now, the reality of just the world and how quantum mechanics work is that in order for us to actually get information from the qubit has to flatten down to a 0 or a 1. So you might say to yourself then, like, well, what's the point? You know, if at the end of the day, all we're getting are zeros and ones, how is this any better than a real computer? Because that's what a real computer already does. The computers in front of us already use zeros and ones. So if we can't get that beautiful superposition out of a quantum computer, why even bother? Those probabilities that you mentioned, that combination of probabilities, is exactly what we do. So imagine, again, my 0 and my 1. 0 and my 1. Imagine we create a algorithm or a new idea for using a quantum computer. And we use those probabilities to our advantage. So I'm going to create an algorithm to figure out, is Brian cool? This is a made-up algorithm right here on the spot, right? And let's say we code the algorithm to have a really, 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 really strong probability that if Brian is cool, it says 1. If Brian is not cool, it says 0. And we run tests on this over and over and over to figure out if it's working or not. And we figure out by, feeding it sample data of, we find a really cool Brian somewhere, and we run the algorithm on him. And now 99 times out of 100, it gives us a 1. So 99% of the time, our algorithm is providing us the right number, right? That probability that Brian is cool, 99% of the time it says yes. So we use these probabilities then for future applications. Maybe we change the name. Maybe now we want to investigate if Dorcas is a cool person. And now we use that same algorithm, and now maybe it's 50-50, or now maybe it's 98%, right? Those probabilities are things that we learn a lot from. And we learn by running these experiments thousands of times. We run them a bunch of times, and we gather those thousands of results, and we look at them in graphs. So by running these probabilities over and over and over, we actually are able to learn a lot from what's happening, even though we're only getting a 0 or a 1. Another really great question. Thank you.
Question. I didn't quite catch the statements about how cold the quantum computer is supposed to be. And I would also like to ask how easily the computer heats up.
Great. Other really good questions. So why does a quantum computer have to be this cold, colder than outer space? It's because these qubits are really fragile. They are very, very, very sensitive to heat, to light, to any type of other vibrations that might send it information. These qubits need to be kept so cold so that they act how we want them to act. Things like heat, like I was saying before. When a qubit gets too warm, that heat, right? Like the hotter a atom is, the more it vibrates. And we know this because solids, like a solid is the type of electron or atom setup where they're all really strongly connected in a lattice. Liquid, and then gas, right? Gas is when they're really hot and they're really excited and they're vibrating a whole bunch. Those vibrations are terrible for trying to create a computer. If the computers in front of you were constantly shaking as you were using them, you would probably say, I don't think I can trust this computer because it's constantly shaking. And so to keep our qubits from shaking, to keep them from moving, we need to keep them really, really, really cold. So that's why it has to be so cold. And then the question is, how quickly do they warm up? I think was your second question. Pretty quickly, right? As we start sending microwave pulses to them, they're getting energy from that. And so our qubits right now don't last more than a second or two. That's how fast our calculations need to happen. And so every time we send instructions to a qubit, once they warm up a little bit too much, we need to reset the qubit back down to 0, back down to its coldest state before we can start using it again. Another really good question. Thank you.
Thank you very much, Mr. Brown. I wanted to ask if these quantum computing processes run on the principle of fuzzy logic.
I'm so sorry. I only heard the first part of that question. Could you repeat it, please?
So I wanted to know if they run on the principle of fuzzy logic.
Oh, on the principle of fuzzy logic. That's a really good question. And I think I'm going to let a future speaker talk about that. For my premise of my introductory talk, I think that might be a little more than I'm willing to get into. But that's a good question to ask a future speaker. Hello.
Hello. Yeah, I wanted to know why the qubits communicate through microwaves and not other waves as well.
Very good question. Our qubits at IBM Quantum, we use superconducting qubits, and so like I was saying with the bridge, right? That qubits are like bridges. The way IBM has set up our qubits, this is the best way to get information to them and get information back from them, is through those microwave pulses. But that is not the only way to talk to qubits. Some other companies have set up qubits where they use light pulses to send information. And even more companies have come up with other different ways to interact with qubits. So we use microwave pulses because for the type of qubit we have built, that is the best way for us to get information to them and out of them. But it is not the only way to do it. All right, awesome questions. If you don't mind, I'm going to jump back into my slides and keep going a little bit further, just because I don't want to take up too much time of your next speaker. But thank you all for the questions. Those were really wonderful. I'm going to skip past this part just a little bit for the sake of time, but what I want you to know is that in quantum computers, you could think of this as a long-term investment. And the cell phones that we have today are nothing like the cell phones that we had back in the 80s. And a quantum computer of today is much more similar to a cell phone of the 80s than it is to an iPhone. So we are really in the beginning of making quantum computers useful. Just like back in the 80s, the 1980s, a cell phone could do so little, right? It could only make phone calls. That was all a cell phone could do back in the 80s. In 2023, a cell phone can do pretty much anything you want it to do. You can send a message to the person you have a crush on. You can buy new sneakers. You can get a ride to somewhere else in town. You can take a picture. You can, there's so many different things you can do. But that's because every year for, 4 or 5 decades, there has been slow but consistent progress and innovation and new things being invented. That is what we need to do with quantum computing as well. Right now, today, we're not there yet. We have a lot more things we need to do to get there, but we're on that path. So you can think of it as, what can we do with the quantum computer in the near term future? And what can we do with one in the far term future? So you may have heard about quantum computers breaking encryption, right? This could hack your iMessages or hack government databases and steal secrets from different people around the world. Encryption is what prevents all of those things from happening. And a perfect quantum computer could, using something called Shor's algorithm, crack today's encryption. So raise your hand if you have heard about quantum computers breaking encryption. Okay, yeah, cool. I saw about half the hands go up there. So that's interesting that about half of you have heard that this is something a quantum computer could be used for. Let's take a quick sidebar here to talk about how encryption even works. The way encryption works, if you don't already know, is computers generate a really, really, really big number. And then they factor that number out. And they, let's say the number is like 278,532,987,127. A really, really big number that doesn't mean anything to me or you as of today. But that big number gets broken down into factors, right? Maybe it's, let's say, number X and number Y. And when those two numbers multiply by each other, they get that really big number. So this is how factoring works, right? Computers take those really, really big numbers and they split it into the factors. One person on one side gets one factor, and the other person on the other side gets the other factor. And so the computer knows if, let's say if I'm sending an iMessage, like an encrypted iMessage or a WhatsApp message that are all encrypted, right? The way your phone or your computer knows that you're allowed to read that iMessage or that WhatsApp message is because you share those factors. You share the things that help make that really, really big number, and your phone or your computer recognizes that. If someone else wanted to figure out what your iMessage said, they would have to factor that really big number on their own. And they would need to ask their computer to take this really big number and figure out what are all the different numbers that can multiply together to make that really big number. That's hard math to do. That's a really tough problem for computers today to figure out. Computers today, when they try to, let me do this. Computers today, when they try to factor that, it might take them a matter of weeks or months, or sometimes even years to factor one encrypted number. And because of that, encryption is really safe. But there's this idea using Shor's algorithm that a quantum computer would be able to factor really big numbers in a matter of minutes. Sometimes less than 10 minutes, a quantum computer could factor a really big number. So that poses a really big threat, right? That encryption that prevents all of our secret files from getting read, that it could be broken by a quantum computer. Well, the good news is the reports of encryption's death are greatly exaggerated. This is a far-term application of quantum computers. This is decades away, because the quantum computers that exist today are not nearly powerful or resilient enough to actually break encryption using Shor's algorithm. And more good news, all the companies that are in charge of creating encryption are already working on new technologies that would be quantum safe, encryption that a quantum computer could not break. So you don't need to worry about encryption being something that a quantum computer is used for anytime soon. But you may have heard of chemistry. Chemistry is a near-term solution, or a near-term way that we think quantum computers could reach quantum advantage. Using an algorithm called VQE, we've actually already gotten scientific results that use quantum computers to analyze different molecules. Here's some of our work from IBM on the cover of Nature magazine, analyzing a lithium hydride molecule. So this is stuff that we think in the near-term future, in the next 5 years, we can see some really interesting progress using a quantum computer. And so if you're not a scientist, what would you use a quantum computer for? Well, we have plenty of quantum games, both educational games and just silly fun games. This one was built by one of my colleagues. It's called Hello Quantum. It's on smartphones. And there's also a game you can play on your computers. It's a Minecraft game that has these challenge rooms built into it. It's called Qiskit blocks. So these are things that use a quantum computer foundation to build games on top of them. The games are all built using classical computers, again, like the one you're sitting in front of, but the games utilize the mechanics of a quantum computer on the back end. You can also use quantum computers to create art. The world's first quantum art and design jam happened in 2021 in New York City. And just this year, we opened an art exhibit in New York City, showcasing the work of quantum artists from around the world. It was really amazing. I got to be a part of it. I was really honored to be there. But for most of history, to access a quantum computer, you had to build it and maintain it yourself. And in 2016, that changed thanks to IBM. We were the first company, and for a long time, we were the only company that let anyone in the world play with our quantum computers and run your ideas on a real quantum device. And that brings us to Qiskit, which is the thing that you've seen maybe up here in the corner the entire time that I haven't actually mentioned. Qiskit is the open source SDK, or the software developer kit, for working with quantum computers. And it's for working at the level of pulses, circuits, and application modules. There are an entire community of folks who are building amazing things using Qiskit, and some of them are in the classroom with you right now. Give a big shout out to all those folks who are Qiskit advocates or who have already downloaded and used Qiskit before. So I'm going to code a circuit with you very quickly here. I know later on you will see some of this as well, but let's just do one really quickly. This is the IBM Quantum Systems webpage. Now, if you want to sign up for this, go to quantum-computing.ibm.com. I'll take this. I'll put it in the chat here just in case anyone wants to see it. And everyone on the computers in front of you, if you haven't already, you go to quantum-computing.ibm.com and you can sign up and do this exact same thing with me. All right, cool. So I'm going to dive into it. I know this is being recorded, so you can follow along and do it afterwards as well. I'm going to launch this thing called the Composer, which is where we see a few different things. I'm going to point out what you're looking at here. On this side, on the left, these colored squares, these things are called gates. And a gate is the instructions that we send to a quantum computer. So things like putting it into superposition or entanglement that we talked about before, these gates are the instructions that make that happen. Over here, these lines represent our actual qubits. So you see Q0, Q1, Q2. You could think of this as the first qubit, the second qubit, and the third qubit that we might be working with. And the lines are a timeline. So as you drag these things, these squares, over to the qubits, you put them on a timeline. And so what you're creating is called a quantum circuit. When you send this circuit to an actual quantum computer, what it does is it reads them from left to right. It says, okay, the first thing that happens is this, then this, then this, then this. We work through the steps on our quantum circuit. And now as I was doing that, you saw here on the right side, this code getting auto-generated as I did more and more things to this quantum circuit. So that's pretty interesting. This code is getting written in real time. This is Qiskit code. That Qiskit, the SDK I just mentioned, right here is where all of that code, like I said, as you drag and drop these gates, it gets auto-generated for you. But if you'd like to see OpenQASM, which I didn't talk about what that is, but if you do know what that is, you can switch between looking at the two different versions right here. And then down at the bottom, you have a way to see some of those probabilities that we talked about before. So I'm going to show you just quickly to demonstrate what this is. I'm going to delete the different qubits. So right now I have one qubit, Q0, and I have the C1 line. That C1 line, that stands for classical. Like I said, when we measure our qubit, it gets flattened into a 0 or a 1. And this C1, this classical bit, that is where it gets measured to. So right now, what I've done, I have my qubit 0, and right now it has a 100% probability of being a 0 when I measure it. That's because I haven't done anything to this qubit. Right now, this qubit's just hanging out doing nothing. All of our qubits, at least at IBM, they always start at 0. So it makes sense that there's a 100% chance that when we measure that qubit, it is a 0. But if I take this H gate, this red Hadamard gate, this is the gate that puts a qubit into superposition. And you can see that probability instantly changes now to being 50% 0 and 50% 1. So now when I measure my qubit, there's an equal chance that when I measure it, it's either a 0 or a 1. I don't know why it's off by just a few decimal points here, but that's the idea here. We're putting it into the superposition. All right. So that is the basics, truly the basics of quantum computing. Let's see, am I still sharing? I think I'm still sharing my screen here. I think I just moved this by accident. Let me put that back up there. Okay. Let me finish by talking about, let me go here. Okay, let me finish by talking about a few last things. So we at IBM really care about building up the future of the quantum workforce. This is the exact reason why me, Brian, I get to be here talking to all of you today. I get to be here because IBM is invested in the success of quantum computing around the entire world, not just in New York or not just in one specific place. We do that in 3 different ways. Open access to our systems. We open source our Qiskit code, which builds that SDK, and by open sourcing our education in as many different ways as we can. Our mission is to support global access to cutting edge technology and give both you, students, and our clients a place to learn, ask questions, and contribute to quantum research. And we believe in supporting the future workforce where you are, not where we want you to be. So over the past 5 years, we've had over 500 college courses being taught with IBM quantum tools. We've had over 21,000 students on campus, just like you today, on campus, participate in Qiskit and IBM quantum events. And through all of our online material, like our Qiskit YouTube page and our textbook, we've reached over 6 million total learners. And building all this out has equaled over $100 million of investment from IBM Quantum into this open quantum community that we continue to help build. We're really proud of it, and that's why I wanted to take a second here and just acknowledge that at IBM, we are really hoping that you are the future of the quantum workforce, that you learn this and that you get inspired to take the next step. We think it's worth it because we know we won't get anywhere without a truly global, diverse, strong-minded group of folks to come into the industry and bring new ideas. So I'm going to skip past the Qiskit Advocate program because I know you will hear about this from Dr. Prakash. I'm going to skip past our internship program, just so you know we have an internship program that I'm really proud of. And the last thing I want to say, I'll go right over here, is the Qiskit textbook is a really great resource Remember, I told you to look for any resource that you can use to help you. The textbook is a great place to do that. You can explore more in the textbook, our GitHub, or our Twitter account. You can get developer certified from IBM as well. You can jump into the Qiskit YouTube channel, which has hundreds of videos, both explainers, interviews, and different ways for you to learn more about each part of the quantum computing community. And the last thing is the Fall Fest, which hopefully we will be running a Qiskit Fall Fest with all of you at KUNST later this year. I'm really hoping that happens. That's going to be it from me. Thank you again for your wonderful questions and for all your participation. My name has been Brian Ingmanson from IBM Quantum. I'm thrilled to have you all here. I'm thrilled that you're starting this 5-day workshop series. I hope you learned something. Enjoy the rest of your workshops and have a wonderful day, everyone. Thank you.
Thank you so much, Brian. We really appreciate your time, and it was a very interesting one as well. Please, I hope you are all enlightened. Great. Give him a high five. Any last question for him? Questions? All right. Brian, someone has a question for you.
Okay.
Hi. So my question is on the uses of the quantum computer. I mean, I feel like it's a pretty big deal, but you listed like barely 5 uses for it. I mean, I feel like a classical computer can do so much more, at least as compared to the way you just presented the uses to us. So are there some things that is just so much capable of, even for like normal mundane people like us, or not specialists? Yeah, so something like that.
Another really great question. I'll start by just reminding you that when the first cell phone was invented, you could have said, all this thing does is make phone calls, right? Like, I have a phone in my house. Why do I need a cell phone? I don't need that. But over time, as more people began to use them and as more innovative thinkers like you started to think of the possibilities, we invented more and more use cases. So right now, today, yes, the use cases are limited, but we hope in the future that the use cases really grow and grow into things that would be, I can't even imagine what they might be, but hopefully really awesome, fun things. So that's the first part of the answer. But then the second part would be other things that you can do today. Well, I'm actually traveling to Barcelona next week or next month to talk about quantum music. People have been creating quantum music on real quantum computers actually for about 2 years now, maybe even 3 years now. That's something that you can do today. People have also been using quantum computers to help look at large data sets or take existing algorithms and try to modify them to be used on a quantum computer. Maybe even trying to invent new algorithms altogether, write a paper about it and get it published. That's another thing that's actively happening today. So you can go the creative route, you can go the academic route, or anywhere in between. But there really are things happening right now today that are useful, interesting things. It's just a matter of figuring out which of those things you like the most and that you want to learn more about.
Hello, Brian. Hello, my name is Caleb, and this is my question. What are the fields of quantum computing that for us college students we can consider if we want to further in the education in that particular field? And my second question is that you spoke about some of the applications in quantum computing. As time goes on, can we discover more applications as time goes on?
Yeah, okay. So first question was like, what should I study to, to go further in quantum? And second was, what other things might be a use case? Is that correct?
Yes, please.
Okay. So the first question, what should you study if you want to get into quantum computing? So this is me, Brian, giving you an answer. This is not IBM official answer. This is not corporate America answer. Me, Brian, I truly believe if you want to get into the industry right now today, you need to have a background in physics, chemistry, or computer science or engineering. Those would be the four today. However, in the future, let's say 5 years from now, our goal is to really diversify and broaden who is getting a job in quantum and the type of degree you need. Many people that I work with right now today have a PhD. That is not a way to grow in industry. If we expect every single person to work on quantum to have a PhD, we will never, ever get to quantum advantage. So one of our goals is to really broaden how many people we can hire and give job opportunities to, maybe who only have a master's degree or only have a bachelor's degree, and figure out what things they could work on. And then on the other side of it, right, the experience as well is something that is crucial for getting a job in a quantum computing company. It's not enough that you just have a certain degree, but you need some type of experience. Our Qiskit Advocate program, which I know I breezed by, is one of the ways that we are trying to give real world industry experience to anyone that can join the Qiskit Advocate program. People from the Qiskit Advocate program work directly with IBM researchers to build real projects that matter, real projects that get adopted by the industry because of how strong they are. And that's really great examples of projects and experience that would help you get hired one day. Internships are another way to do it, but open source, submitting projects to the GitHub, submitting pull requests and adding your own code to Qiskit, that's another thing that you could do to really start getting that experience and getting a really broad skill set that will help you get there. So that's my short answer. Right now, today, a little bit more limited, but hopefully in the future, we have a much better way of getting there. And then your second question about use cases, I don't know, man, like hopefully we have some really amazing new ideas. That's really one of the big reasons I love working in this industry, is because we don't know. We don't know yet what might be the best use case for quantum computers. And I really am hopeful that one of you is the person that figures out what that is. But it's fun.
All right, I have a last question, and this is my last question. And I heard that the quantum computing field is divided into 3 categories: the science, communication parts, and they have the material parts, and they have the people with working with algorithm. Can you explain that?
So okay, I think I might not have heard that correctly. I heard the 3 different categories: science, communication, and I'm sorry, I couldn't quite hear everything.
All right, so it was 3 categories. So we have the one that work with the writing the quantum algorithms. Then we have the one that works building the structure or creating the qubits in the lab. That is the materials sciences and things. And you also have the one that deals with the communication to the people. I don't know whether I get.
Yes. Okay. So Yes, those three categories are correct. We have software-focused people, we have hardware-focused people, we have communicators, but we have a lot more than that too. We have researchers whose job it is to, excuse me, to think about the possibilities that maybe we haven't actively explored, to do a lot of theoretical work and a lot of theoretical testing that then maybe our software and hardware teams try to actually put together. So there's that side of things. There's also the business side of it. You know, like quantum computing is a business. It is an industry. There are startups. There are big companies like IBM and Google, and there's a lot of smaller companies in between. All of them are businesses that are trying to generate funding, that are trying to work with clients, work with investors. So there's the business side of everything as well. There's also a big side, you know, this community side, like what my main job is. It's not, it's somewhere in between communication and community building, but it's everything from working with students to working with professors and giving them new tools to teach, to, you know, creating our YouTube channel, creating our textbook, all of that type of stuff as well. And then another last maybe part of the team that I would mention is that layer in between the classical computer and a quantum computer. There's a whole team of people that need to figure out, when I send a instruction from my laptop and it goes to a quantum computer, what is the best way to transpile those instructions so a quantum computer can understand it? What's the best and most efficient way to reduce the amount of errors that might show up, or the most efficient way to actually write those instructions? So that's another really strong part of the team too. So there really are a lot of different parts that happen among IBM and other industry groups as well.
Right. Hello, Brian. Thank you for the presentation. Sticking, okay. Please, can you hear me? All right, sticking to the point of taking IBM achieving quantum advantage. According to my understanding, at IBM, there are researchers, scientists, and industry heads working really hard to make the quantum computer much better. And this means achieving perfectly 50-50 advantage. Let's talk talking about zeros and ones, right? And that would mean you perfecting the information you get back from the probability storm that we spoke about during the presentation. But then, according to my understanding, the qubits, we have control over the qubits, but you don't have control over the probability storm. So whatever information you get back, turn it back into zeros and ones to deal with. So in order to gain this quantum advantage, this would mean you gaining control over this probability storm and the information you get back, and perfect the results that are returned from this probability storm. So my question is, what efforts are being put in place to perfect or have control over whatever goes on in the quantum realm in terms of quantum mechanics and quantum physics?
Yeah, good question. Thank you very much. Because my talk was definitely a very beginner level, there are some things that I left out. One of them is this idea called quantum interference, and it is exactly what you're talking about. So interference, right? If I draw a wave, I don't know if you can see this wave right here. We have both good interference, constructive interference, and bad interference or destructive interference. So on a wave, if we set up an equal wave going the opposite direction, right? That would, like this, that would destroy our information, right? So we're taking this first wave and we're giving it, you know, a destructive wave on top of it. So boom, we're getting rid of something. On the other hand, you could also take a wave and you could add to it, right? You could amplify it by giving it constructive interference. So this idea of destructive interference and constructive interference, or taking things we don't want and getting rid of them, and taking things we do want and getting more of them. This is exactly what some of our team members are doing, right? This is exactly what you were asking about. How do we get those zeros and ones to mean something? How do we help that get to advantage? This idea of interference is what many of our algorithms are trying to do, right? Our algorithms are trying to say, for example, that really stupid idea I gave before about the "is Brian cool" algorithm. If I know my algorithm needs to be really, really strong, I need to know that the parts of the algorithm that are not working, I need to write a new part of it to get rid of that automatically. And the parts of the algorithm that are working, I need to write parts of the algorithm to amplify that. And so when I run my algorithm 10,000 times, this idea of it automatically getting rid of the bad stuff and giving us more of the good stuff, it just happens as part of the algorithm. And so if I run it 10,000 times, now I have this huge data set that I can look at and figure out, was that working how I wanted it to work? So yes, is the answer. Yes, we do have people actively working on that. It's called interference. I do think one of your future speakers will talk more about it. I just didn't have enough time in my part to talk too much about it. But great question. Thank you very much.
Hi. So I have a question. You did a little demonstration using the computer for us. Now, I'm curious, is whatever is being done here, like running real time on your IBM quantum computer, or this something like a simulation? Because you said like millions of people get to use this. So like, is it real time? Do you just, whatever I input here, I get the results directly from, like you said, the computer is in Denver or somewhere like, so yeah, that's what I want to know.
Yeah, really good question. So right here, I'm doing the simplest thing I can. I'm putting a qubit into superposition and I'm measuring it. And in real time, you see that probability change, right? This is a simulation down here. So this is a classical computer just guessing about what would happen. So this down here is not really running on a quantum computer. If I wanted to do that, I go up here to the setup and run button, this blue button in here in the top right. And now I can see the different quantum computers that I actually have access to. So these are all the different computers. You can see this one, IBM Perth, has 215 people waiting in line for it. This one, IBM Manila, only has 33 people waiting in line for it. And this one, IBM Peekskill, I'm not going to use that one, but this one has one person waiting in line for it. So the different quantum computers have different, you know, we call these queues of people waiting for them. But if I didn't want to wait, I could run my stuff on a simulator. And these different simulators have taken data sets from quantum computers and can recreate those based on your own hardware. But let's say I want to run this on a real quantum computer. I choose Lima. I'm going to run this. I'm going to call this, what's this called? Oh, QMP demo. Okay, so I hit run. Now over here, I can look at my jobs. This one is in the queue right now, getting ready to be run. It'll probably take, you know, a couple minutes because you saw there's other people in line ahead of me. But now I'm in line to actually run on a real quantum computer. Here's one I did back in January. and you can see the actual results from what I ran back in January. This was the exact same type of thing I ran. This was a circuit. You can see it right here. I've actually put it in superposition and entangled it, but I ran this 1,000 times. I had one circuit that I ran 1,000 times, and then this was my data I got from that circuit. So yes, you can run them on real devices. It just takes a little bit more time because we're waiting in that line. And I only rushed through that part. I know I rushed through it because I know every speaker after me is going to be doing the exact same thing with you. So I didn't want to take too much time talking through it.
Hello. Please, you said QUBIT give us the information, like the measuring of the QUBIT, that's the output of the microwave processing. So please, does the nature of the QUBIT affect the measuring of the QUBIT?
Does the nature of the qubit affect the measurement of the qubit? Well, I'm sorry, when you say does the nature of the qubit, do you mean like the way that we build it?
You said the QUBIT should be warm. QUBIT?
No, correct. Okay. Yes. Okay. Sorry. Yes, it does. It does, and that is an issue. We call that noise or errors, right? And there are hundreds of different types of errors or noise that happen. Sometimes it's because a qubit is too warm, like you were just saying. Sometimes it's because a photon from a ray of light somehow got in and hit our qubit. Sometimes it could be because a cosmic ray from outer space got somehow interfered with our qubits. Like, they are so sensitive. They are so sensitive that any little thing, a speck of dust, could change how our qubit actually gets measured. So that's one of the reasons why we run experiments so many times, is so we have enough results to make sure there wasn't anything like that that happened. But it is also a reason why we're constantly doing research to make our systems stronger and more resilient, because right now they are just so sensitive and so fragile that easily a qubit can get messed up and give you the wrong answer.
Yeah, hello. Yeah.
Hi.
Please, when you're talking about the advantages of the quantum computer, you made mention of its application in the chemistry field. I was asking, at the moment, we perform DFT calculation on supercomputers. I was asking if it would be possible for us to perform a DFT calculation on the quantum computer.
Yeah, it is. You can run it. So there's an algorithm that I mentioned called VQE, or Variational Quantum Eigensolver is what it stands for. And the VQE algorithm is meant to be run on a quantum computer, and it analyzes molecules. I mean, it has to be a simple molecule right now. It has to be a small molecule like lithium hydride. But yes, you can. And we actually have tutorials that teach you how. I'll find one for you and I'll put it in the chat in just a minute. But yes, you absolutely can.
All right. Thank you very much, Brian. So my question is a follow-up to what the brother just asked right now. In my lab, from the chemistry background, we do simulations, biomolecular computations, where we check protein ligand interactions, protein folding. And we currently do that with Lingao, a high-performance computing center in South Africa. Sometimes our simulations could take several weeks. So I'm trying to link what we do in the lab to what we are learning here in quantum computing. If we could use quantum computing, could we tap from your resources as the chemistry department here in order to do our simulations?
So in the future, yes. right now today, our computers are not powerful enough to do protein folding. That is, I wish we were, right? That's my hope and goal. But right now, our quantum computers are still working on kind of basic molecules because they're just so limited, and we're still making them better and better. In the future, hopefully, in 4 or 5 years, the answer will be yes, that is something you can do. But as of today, we just don't have enough stability of our qubits and strength of our systems to handle a full protein folding synthesis. But with that said, we do have, let me pull this up for you. We do have that built into Qiskit. So here at the end of last year, you can see this is from November of 2022. We have a Qiskit protein folding module that we have built. So this is something that people are thinking about and actively trying to work on. Like I said, you should explore this. You should check it out and see, based on what you're doing, would it make sense to try and use them? But if it does, you can use any of our open systems to run this, to run your algorithms on. So this is something that our scientists do care about, is I guess what I want to say. Okay, so thank you all. For the sake of time, I've taken up an hour and a half, and I know Dr. Prakash has just as much amazing information. I don't want to keep taking up too much of his time here. So I want to say thank you again to everyone for having me. Thanks for letting me be your lead-off talker. And I hope you learn some amazing things over the next 5 days. And like I said, use that advice. Don't worry if this goes over your head. Ask questions, use this time to your advantage, and really have a great time. So thank you again, everyone. Have a wonderful day.
Thank you so much, Brian. Is it exhausting? No, not at all. Okay. So can we get just stretch your hands and your legs before the next speaker comes in. Just get up. Get up. Yeah, just stretch. Just stretch. It's not good to sit for long hours. You know that, right? All right. Okay. All right. You can sit. Thank you so much. And I think we are introducing the next speaker, Prakash.
Yes.
All right. Thank you so much for being patient with us and holding on. It's actually 9 p.m. in India now, so it looks like he has been waiting for long and he might need to get some rest. So Prakash, we won't waste much time. Participants, our lecturer for introductory quantum computing now is Dr. Prakash from India. Prakash.
Yes, actually, I'm very much eager to meet you people. So that is the reason what even I'm maintaining my patience.
Yeah, so Prakash, we can't see you. We want to see you.
Yeah, I'm audible. I'm audible. Hello. Yeah. You guys need a break? You guys needed the break for 5 minutes? Or shall we continue?
You can start.
We can start.
Yes.
Okay. So am I audible? My voice is good? let's start. See, I am waiting for a response. Am I audible and my voice is good? You guys able to hear me properly?
Yes, very audible.
Yeah. So let us start. So is it visible? Okay. So you guys able to see my screen over there?
Yes.
Okay. Actually, I'm very happy to see so much of quantum enthusiasts. Right. So take a look. So I am Dr. P. Satyaprakash. The reason why I am willing to deliver this content, right? I am a part of quantum educator of IBM. So my primary job is to connect students specifically with Qiskit. Right. Okay. So let us start with why we need quantum computer. Take a look at this. What you're able to see from here. So why we need quantum computer, gentlemen? So the reason why we are going behind any quantum computer. So what is the difficulty which we are facing with classical computer? Anybody from your audience?
Hello.
Yeah.
The reason I think we need a quantum computer is because apparently it's supposed to make computations faster than our normal and classical computers, and so it's worth the study.
Okay. So okay, halfway you are near to the question. But what was happened? So if you look at the definition of classical computer, so what does a classical computer mean? See, I think you people are from mathematics background, physics background, so there are interdisciplinary enthusiasts available. So in order to bring you to bring you to the stage, I need to provide the what is exactly behind the classical and what is there inside quantum, right? So there is a law which is meant for what? Number of components present in a board or a chip. So it is called what? Moore's law. You guys heard about, right? If people coming from electronics background, so they may know what is that? Moore's law. So there is a severe difficulty with a Moore's law states that Intel failed in nano size processor. You guys know. Right. So even with respect to number of components present in a chip is not able to produce a feasible computing complexity. Right. The main problem with the classical computer is what? Even though we can able to incorporate so much number of components in an integrated chip. It fails to what? Provide a computing speed which match quantum is what? Nowhere it is matching with quantum computer. So we have so many supercomputers, right? So classical computer can perform only specific task in a better way. But classical cannot able to do certain operations. The first and foremost, if people are somebody from mathematics background, they know what is factorial, factorization. If you provide a small factorization problem to a quantum, to a classical computer, then what happens? You guys know. It takes how long to solve a factorization problem by a classical computer? Still, we cannot able to what? We cannot able to predict how long a classical computer used to solve a factorization problem in mathematics. So they found out a different kind of computing called quantum computing. So how to define a quantum computing? So let me tell you the technical definition of classical computer. So if there is a flow of electron from equator to which part of a hemisphere? Suppose if the electron travels from your equator to northern hemisphere, it may be represented by 0, right? The next part, if the electron travels from equator to your what? Southern hemisphere, it may represent 1. The point is what? In classical computer, it can be either in one state at a time. It may be 0 or capital OR. So what is capital OR in physics? 0, capital OR and 1. So what does it mean? So what does that mean? Classical is 0 or 1. So what is it R? See, R is logical. So it means what? Logical R. What is logical R and logical AND? So definitely it may be 1. Definitely it may be what? 0 or 1. So that is the meaning of what? Your 0 or 1. Right. The first definition for your QC is what? In a layman way, definition for QC. Any guys? With respect to 0 or 1, tell me the definition for quantum computing. Any guess? It is 0. It is what? 0 and what is that? What is this AND stands for? What is this AND stands for?
Hello.
Yes.
Logically speaking, the logic AND stands for the output, both outputs being 1 or both outputs being a 0.
Yes. So what is the major phenomena behind the quantum is what? At a time, it can be in the state of 0 as well as 1 is possible. How? Any idea?
Please repeat the question again. I didn't get you.
See, the layman definition for quantum computing is quantum computing can be able to withstand in a state 0 and 1 in the same time. See,
Yes.
if you speak in a probability, So suppose if you take a qubit, so qubit is going to be the basic component of any quantum computing. So that qubit maybe contains 40% probability of 0. And if it is going to be 40, the remaining 60% is going to be 1. Or if you take in another way, 50% of 0 is possible and 50% of 1 is possible. If not, 70% of probability 1 and 30% of probability 0. So this is the basic definition and what basic phenomenon behind any quantum computing.
Okay, thank you. That's clear.
Yes. So what is it? So if you understand what is a classical 0 or 1, people used to say what binary. Yeah, obviously binary means 2, right? And if it's tri means 3. So what does it binary? 2 values represents your flow of electron from equator to any part of the hemisphere. If it is northern, it is going to be 0, or what if it is southern hemisphere, it is going to be 1. But anything, but at a time, what is possible? It may be 0 or 1, but it cannot be what? 0 and 1. So this is what a definition for what our quantum computing. Right. Then what are the basic building blocks of classical computer? Building blocks of quantum computer. If you look at any computer, what will be there? There will be a central processing unit and what? A monitor and various input devices, right? Right. If you come to quantum computing, still now quantum computing is not stand alone. What is that? Quantum computing is what? Not a stand-alone component. It is hybrid. If we want to work with any quantum computer, so what is that? In which mode it will operate? It will operate with the help of a classical computer. Then what? The remaining will be carried out by the quantum computer. It means if you provide any operations, who fetches? Classical computer's central processing unit fetches the operation. Then after processing, it gives to where? It gives to QPU. It gives to where? QPU. QPU stands for quantum processing unit. So now you got why it is hybrid. The quantum computer cannot able to do what? Function on its own. Still now, which are all the quantum computing components we have, right? It is depend upon the classical counterpart. So which receive all the instructions from where? Normal CPU. Later it is given to where? Later it was given to your quantum processing unit QPU. Right? So then if you ask me the basic building blocks and protocols behind QC, the first point is going to be qubit. So above qubit, there is a protocol called superposition. What is that? The first protocol is going to be superposition. Then with the help of superposition, we need to combine 2 qubits to produce entanglement. This superposition and entanglement are 2 important protocols of quantum computing. And there is a third protocol called teleportation. Superposition, entanglement, and there is teleportation. Right. Got it? So what are the basic protocols? Superposition, entanglement, and your teleportation. Right. So now let us look at what is superposition. Right. So what is that? Superposition. So what does that mean? Example for superposition. Let me tell you 2 examples for superposition. Suppose we are having a coin, right? A coin may contain two sides. One is belongs to head side. The other one is what? Tail belongs to the next side of the head. Means a coin contains what? Two sides. If you go behind classical computer, so what does it mean? In the coin, either you can face head from a side or we can face tail from other side if it is going to be classical computing phenomenon. Okay, but in case of quantum computing, what is possible, right? Once we start flip the coin, so then what will happen? Once you start flip the coin, then what will happen? It started, it will start spinning, right? So we cannot be able to see which side it is. Yes or no? Yes or no? Yes. So that is what one real-time example for what? Superposition. So the coin, when it is in the spin, we cannot able to see the either of sides, whether it is head or tail. So if it is keep on spinning, right? That spinning is what? Exactly 0 and 1. Example for superposition. So let me tell you one more example. So there is a room in the, so there is a building, two-storied building. There is a ground floor and there is a first floor. In the first floor, there is a room. So that room contains a light, right? But we are in the ground floor. So is it possible for you to predict whether light is switched on or off? In a layman way, we are in the ground floor. So there is a room in the first floor and it contains one light, right? So now my question is what? Whether it is possible for you to predict whether light is on or off. Is it possible? So when it is going to be possible, check whether the light is on or off. After climbing up, enter into the, climbing into the first floor, and if you open up the door, then only we'll come up to know what? Whether the light is what? On or off. So then people used to say, this coriander cat present inside a box. They used to tell for what? Example for superposition. So in order to understand the superposition, we should have an example, tossing a coin and the light which is glowing in the first floor. Then what? When we enter into the room, then only we'll come to know whether light is on or off. But being a observer from the ground floor, we may not know it is on or off. It may be on and what? Off. It is possible, right? So that is another example for superposition. So technically these quantum people used to explain with scavenger cat. So the cat available in the box, in which color it will be, brown, black, right? So that is another example for quantum superposition. Clear? So now we have seen two basic blocks, qubits and superposition. So let's go back to qubits. What is this qubit? What is this qubit? So qubit is the basic building block of any quantum computer, and it is represented by 2 to the power n. What is that? It will be represented by what? 2 to the power n. Having a single qubit will not produce much effective results. So then what should be done? We need to entangle qubit. What is to be done? We need to entangle two superpositioned qubits to form what? To form entanglement. To form entanglement. Right. So then tell me, what is technically the superposition? So we have seen what? It is combination of two states. Right. how to speak in terms of mathematics? How to speak this in terms of mathematics? How to speak in terms of mathematics? So in superposition, probability of 0 is going to be what? 50%. And the probability of 1 is going to be what? 50%. Yes or no? Am I right? But actually what is inside, right? Let me tell you. See, because of pure quantum randomness, right? We cannot exactly say it is going to be 50 and 50 for 0 and 1. It may be 60-40, it may be 40-60, it may be 30-70, 70-30, right? Because why? Quantum is all what? Randomness. Nature is what? Richard Feynman told what? Quantum is what? Sorry, nature is what? Quantum. So this phenomenon is how it is possible? Because purely it is randomness. So if you have a quantum source, it will generate 0 or 1. It is purely going to be what? Randomness. The fact behind this quantum is what? Exactly the nature is going to be what? Randomness. So it is what? Generating superposition, right? So that is what a coin being flipped is head, is tails, mix of both. This diagram speaks that. And scientist cat next to some poison is alive or dead. A cube, you see what is face in front, the blue or orange. This is also an example for what? Our superposition. A spin, a future of an electron roughly like a magnetic field. Hard to express in classical world. What is not possible to express? Superposition is not possible to express in classical computing. Next is what? Entanglement. Right. Entanglement. So generally tell me what is the English meaning for entangled or entangle. Am I audible? Am I audible?
Yes, you are audible.
Yeah. Let me tell one famous example for entanglement. You know, marriage. Exactly, human marriage is what? Example for what? Entanglement. Suppose there are two qubits, right? Whatever happens for your first bit, right? It will impact your second qubit. Right? In marriage, it is happening, right? Whatever happens to your husband, it impacts your wife. In general, don't go specific. In general, yes or no? So one real-time example is what? Marriage between a male and female, right? So whatever happens to this male, it is what? It is going to impact his counterpart female, right? So entangle. So if there is two qubits which is in superposition, if it tied up, then it will generate what? It will generate a magic. So this protocol is called what? Entanglement. This is a second important protocol. What is that? Two superpositioned. If you ask me exactly, equally superpositioned qubits to form entanglement to do magic in terms of quantum technologies. Did you notice this word? Equally superposition. So what does it mean? Equally superposition means that time qubit will be behaving what? 50% belongs to 0 state and the 50% belongs to which state? 1. This is what exactly equally superposition. So equally superposition is an important measure towards any qubit. Right? How to achieve that we will see in later part. So this is what? Entanglement. So I told you, right, marriage. So what is this? The first one is what? The male, and the second one is what? Going to be female. If you take one out, so what you can able to hear? If you collect the feedback from the male, you can get what? What has happened in their relationship? Yes or no? Need not to measure the two. We can simply measure from one. So this is what? Entangle. So this is here what? Take a look. Two qubits combined together to produce entanglement. So how to measure? If you measure one among them, we will get what is present inside that qubit. So whatever it is there in the qubit 0, that will be what? Given to the qubit 1. How to measure? We need not to measure the both. If you measure one, we will come to know what is the state present inside the qubit. So what does that mean? 100%, whatever you are what? Whatever you are reading from the qubit 0 is what? Going to match with the second one. Right. So now I have a question for you guys. Suppose %, suppose what? 70% of qubit 1 is going to be probability 1. Then what will be there in the second qubit? Here 70% refers to probability of state 1. What is qubit 0 contains? Qubit 0 contains 70% of probability 1. No. Entanglement. We are not speaking about the remaining probability. We are speaking about entanglement. Go back to the husband and wife. Whatever the impact made it from the husband, it will what? It will be given to the wife. So what is it? What will be there? 70% of 1. Why? That is what? Entanglement. That is what we are learning from this figure. Yes or no? Measure one, the other one will match. So what we measure? Look at the statement. We measure it is going to be 70% 1. Yes or no?
Yes.
So then what will be here? The other will match is what? Means what? It is also going to be what? 70% of state 1. Right? Shall we move further? Any doubts so far? Any doubts? Okay. So I can conclude. We will move further.
Hello.
Yeah. Right. Here it is a twist. Right. Now I would like to interact with you guys. I need your interaction without fail. See, how many of them from here wanted to program quantum computer?
All of us.
All of us, right? So all of you guys wanted to program quantum computer, right? Then in order to program quantum computer, so what are all required? In order to program quantum computer, so what is required? You are from mathematics, you are from physics, you are from chemistry, you are from mechanical, you are from electrical. It's what? It is not going to make any sense, right? Let me show you, right? Whenever I spoke with my undergraduate students or postgraduate or any students, right? They always what? Misconception what they are going to do with quantum, right? So look at this statement. What is written here? Misconception towards quantum learning. What is the first misconception? It is not required to build or to research with any quantum technologies. Yes or no? Many people break their heads what? They are going to do any research with quantum technology. No. In order to do quantum programming, what is required? No research knowledge is required towards what? Programming the quantum computing. Agree with me?
Yes.
Thus, next look at the second point. Quantum computing is not going to be a conventional or classical computer killer. Yes or no? Yes. Why? Quantum is going to be hybrid. Yes or no? No quantum computer is going to what? Replace the entire classical computer. So this is the other one. Next, what is it? Run all computations on a quantum computer. No. As I said or mentioned earlier, only part of your operation is going to be what? Run on your quantum computer. Agree with me? Then most of the time I seen people, whether it's undergraduate or post, right? They are comparing the laptop or desktop's clock cycles with a quantum computer. Will it matches? No, never. We should not compare a quantum computer with laptop or desktop clock cycles. You guys, enthusiasts, agree with me? These are all the general misconceptions toward any quantum computing learning. It makes sense? It makes sense? Agree with me or not? Or is there any deviation? So only thing is what? All you need interest, all you need your focus. Then what is possible? You can learn quantum programming the quantum computer. Like how? Let me tell you. We will enter into the next. So right. So what is this? Reality of quantum computers. So what is the beauty of computer science? The beauty of computer science is going to be what? Abstraction. Who developed C programming? We don't know. Somebody have developed and there is some implementation. We are starting use of it. Yes or no? So without knowing the actual implementation, we can utilize the behavior. Yes or no? This first point is very, very important. What is the beauty of computer science? It is going to be abstraction. Without knowing the actual implementation, we can start utilize the behavior. If you take C programming, you are able to run the code, right? What is present in the compiler does not matter, but we are able to run the code, right? That is the first thing towards what? Reality of quantum computer. Then what is the other thing? Dramatically extend, speed up calculations. So what is the beauty of quantum computer? If there is a problem exists exponential, so it is dedicated for what? Quantum computing is not dedicated for those kind of applications. NP-hard problems, exponentially what? Exponentially growing problem means factorization. So factorization is what? Reverse tree structured. Keep on what? From root, the keep on branches will what getting grown. That is what it is meant for, dramatically extend, speed up calculations. Right. So then what is the thing? In programmer's point of view, quantum computer is what? Really a co-processor. So what is it then? Quantum computer is what? QC is going to be a co-processor. Quantum computer is what? Really a co-processor. So earlier I mentioned, you remember QPU. What is QPU? The unit refers to device on which our code samples run. QPU stands for what? Device on which our code samples run. So what is the process? As I told, first it will run on classical computer, then central processing unit issues the operation to quantum processing unit. It's nice, right? Yes. Okay. Okay. Next, you asked. So yes, I was noticed that while you guys were discussing this beyond, you are asking what are all the quantum computing applications. So the main quantum computing application: Qiskit nature, Qiskit finance, Qiskit machine learning, finance, learning, nature, and chemistry. So Qiskit mainly focuses on these 4 applications: machine learning, finance, nature, and quantum chemistry. And what is that? Quantum chemistry. So I took this from Qiskit. So what is a quantum computer applications meant for? Majorly they are focusing with nature application, chemistry application, machine learning application, and the finance application. Any guess why these applications? What about the data available in finance? So internal components in nature, electronic structures, extended state solvers, lattice model. So which is what? Subcomponents of quantum computing, particularly focused on Qiskit nature. Next, subcomponents of quantum computing application: Qiskit finance, quantum amplitude estimation, portfolio optimization, Qiskit optimization. So where it contains quadratic programs and viewer optimizations. Then QML, machine learning task, internally contains QNN, stands for quantum neural networks, neural network classifier, PyTorch for GAN implementation, torch connectors, and hybrid QNN, quantum convolution neural networks, and Q. So these are various modules comes under that particular application. All right. Then various types of quantum computing technology. So what are various, right? Superconducting is what? One technology belongs to what? A type of superconducting. Sorry, one type of quantum computing. The main is what? In that superconducting, IBM quantum falls under superconducting category. Then there is another business leader who they are evolving with superconducting is going to be Rigetti. Then there is a type of, another type is going to be trapped ions. So IonQ, Quantum, and AQT, these are all the players who falls into trapped ions category. The next category is going to be spin Q, quantum inspire, cold atoms is what? Qiskit cold atom provider. And platform going to be Azure Quantum is what? Is an Amazon's flavor of computing. And the simulator QQuantum belongs to NVIDIA. Accessing what? This is accessing quantum computing systems in a different way. Right. Next, who are all having commercial quantum computers? If you ask who are all having commercial quantum computers, Honeywell is having commercial quantum computer. Rigetti is having his own quantum computer. IBM is having their own quantum computer. Microsoft is having what? Their own commercial quantum computer. And Google is having his own quantum computer. Right, who are all Honeywell, Rigetti, and so on. So, but they are all reputed companies those who are having commercial quantum computer: Honeywell, Rigetti, IBM, Microsoft, and Google. So you can choose anyone. It's up to you. It is not restricted. You should learn only IBM quantum computing. You should learn only Rigetti. It depends upon your convenience. Honeywell, Rigetti, IBM. Why IBM is so popular? Most of the resources are what? Free. Anybody can able to access. That is the reason what IBM is most exposed with respect to the remaining competitors: Honeywell, Rigetti, Microsoft, and Google. Right. So these are all what? A normal part. So what is there in the research? What is there in the research? Software and hardware. Now we will come here. What is that? Country-wise investments for quantum computing. So which are all the countries in the world who are interested in quantum computing. So who is the bigger figure? Any guess? There are so many 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are almost 20 countries were in the quantum race. So who invested maximum? Take a look at the diagram and tell me. If you ask me, two highest, one is United States of America, the other one is China. These two countries are what? Invested huge, and they are the large players in quantum computing. US 1.2 billion, and look at China, it is what? 15 billion. Netherlands, Denmark, Sweden, Finland, Germany, Austria, Russia, South Korea, Japan, Taiwan, Thailand, Singapore, Australia, and Canada. What? These are all the globally country-wise investment for quantum computing. Next. Right. So this is here what it makes difference. Okay. In order to learn quantum computing programming, so what is the prerequisites? Right. The quantum computing programming prerequisites are going to be familiarity with programming control structure. The first and foremost thing is what? Familiarity with programming control structures. If you ask, it is if, else, while, and for. So these are all what? Various control structures of any programming. C, C++, Java. If you take any programming, these are all going to be what? Programming control structure. Next, out of all, the next, what is required? Programmer level mathematics. Programmer level mathematics. Mathematical functions, trigonometric functions, conversion of binary numbers from binary to decimal and octal. So we should know number conversion from which? So number conversion from binary to decimal, binary to octal. These two are going. This is another prerequisite for learning programming the quantum computer. Programming the quantum computer. The next one is what? Complex numbers. This is is quite interesting. It is what? Quite interesting. Now I have a question for you guys. Which programming language directly supports complex number? C, C++, Java, Python. Which programming language directly supports complex numbers? Yes. C does not support, C++ also does not, Java also does not. So Python is what? Python is the only programming language directly supports the implementation of complex number. Agree? Agreed. Yes. That is the reason majority of the quantum software evolve around Python. That is the reason what? Majority of the quantum programming software evolves around Python. If you take Qiskit, what is base for Qiskit? Qiskit base is going to be Python. Qiskit base is going to be Python. So what is required for learning programming the quantum computer? Basic programming control structures, mathematics, mathematical function, trigonometric function, number conversion, complex number, then computational complexity of an algorithm, big O notation. This is what used to represent what? Short and simple. Short and simple are what? Short and simple and what? Write once, run multiple times. Write once, run multiple times. Short and simple, less space and much effective. These all things which comes under big O notation. Which comes under big O notation. Right. Then maths background guys can tell me what is that? Math required for what? Quantum computing. Hey guys, give me a minute. Let me take a break for 2 minutes, if you don't mind. I need a break for 2 minutes. So I need to fix up my my dinner. Let me fix and I will come back. Is that fine? Okay, give me a minute. I will be joining back in 2 minutes. Hello. Thanks for your patience. Right. Let's start. Yes. Mathematics part, right? The basic thing required for the quantum learning is going to be sets, vectors, and tensors. What is set? So set is what? Elements, natural elements which contains inside a bracket. So what will be there? Inside a set, there will be elements in a natural order. It depends upon the set. So empty set, finite set, infinite set, and a singleton. Look at the last one. What is a singleton set? These are all very known, but the singleton is not very new, right? What is singleton? Whenever you go behind that particular set, there will be a particular number will be there. Maybe any number, 5 or 6 or 7 or 8, 9. But whenever you retrieve the set, the value is what? Going to be the same. Right. That is what? Singleton. I'm sorry. The next one is what? Vectors and tensors. Very interesting, right? So what is vectors? What is the vector? So I think you people know the definition, but there is a connection between these two, vectors and tensor. Right. Let us look at it. In later part we will see. The next one is what? Matrices. So matrices, right? What is why and what purpose matrices required? In order to represent the, right? Let this come from here. So vectors and scalars. Scalar is what? Only having magnitude, and vector is what? Having both magnitude and direction. So in order to represent a resultant vector, what is required? The quantity which is multiplied by the scalar and which will arrive with the resultant matrix. So that is the reason we are putting only the coefficient value in matrix form, right? In order to handle a vector, what is required? The scalar quantity of the vector represented with the help of what? Matrices. That matrix may be row matrix, column matrix, singleton matrix, null, rectangular matrix, and square matrix. Fine. Okay. Let's go further. Right. So here we have left out one thing, tensor, right? So let us look at it. What is tensor? A tensor is a multi-dimensional array. Tensor is what? Multi-dimensional array. Whether it is a one-dimensional or else it may be two-dimensional. See, you people aware of array, right? Or you need clarification for array? Anybody from your side needs clarification for array? Okay, no. Let's look at it. Scalar is what? A number simply denoted by only, it represents magnitude. The second one is what? Vector. Contains magnitude and your directions. You can represent with the help of two axes, X and Y or Y and Z. It's up to the convenience. The next one is what? Matrix. It have row and column wise contents. Row and column wise contents. What is next? Matrix of matrix, or else what? Each component is what? Having a matrix or amplitude and direction. That is called tensor. Look at here. One-dimensional tensor is a vector. Two-dimensional tensor is matrix. Each matrix, it is 1, 2, 1, 2, 1, 2, 1, 2. So what? Scalar, your vector, your matrix, and our tensor. Right. Various software available for quantum computer. We all well known about and well aware of what? Qiskit, Quantum Information Science Toolkit. What is this? Qiskit stands for Quantum Information Science Toolkit, which belongs to IBM. The next one is what? QCE engine. It is a simulator which belongs to what? A general group who is what? Willing to do demonstrate some quantum computing phenomenon is what? QCE engine. The third software is what? Going to be Circ. So who is the contributor of Circ? Any idea? So Google's software is what? Going to be Circ. The fourth one is what? Q#. So this is a language dedicated by Microsoft for what? Implementing quantum computing. The next one is what? Going to be Penny. It is a software offered by Xanadu. There is a commercial business entrepreneur who is that? Their name is going to be Xanadu. Their name is going to be Xanadu. Right. Now we are what? Falling into the Qiskit. Right. So what is Qiskit? So you people are very eager to learn what is Qiskit, what are all the components of Qiskit, how to install, blah blah, right? Right. Quantum Information Science Toolkit, and it is what? It is called as a stack. Right. How to work with Qiskit? So we all know the base behind the Qiskit is what? Python. Right. And the sophisticated user interfaces for Python is what? Jupyter Notebook. Jupyter Notebook. Python using Jupyter Notebook. And here it is a link. You can what? Install your Python and various integrated development environment tools available for Python. So that is the reason I told complex number can be directly handled by Python programming language. So we are focusing on Qiskit. Being a IBM quantum educator, it is my job to what? To disclose, advertise, and preach about Qiskit activity. That is my primary job, being a IBM quantum educator. Specifically to which community? Students, researchers, high school students, etc. Specifically using Qiskit. Right. Then how to install? QUBIT is what? A package picker present in Python to what? Install any modules. So how to install? We need to provide pip install Qiskit. So if you provide this, then what will happen? If you provide these lines, then what will happen? There will be few lines of installation scrolling up, and finally it will stop. Once it is successful without any error, then we need to type what? We need to type import Qiskit. Import Qiskit. Right. Yes, it is successfully installed and we have imported. Now we need to what? Check the version. So how to check the version of Qiskit? In order to check the Qiskit version, we need to invoke the function along with Qiskit object. Along with Qiskit object, dot operator, double underscore, Qiskit underscore, version double underscore. What is it? Qiskit object dot double underscore Qiskit underscore version double underscore. Right. Once then after that, if you hit enter, then what will happen? Then you can to see few lines of code 1, 2, 3, open bracket as well as close bracket. So which Qiskit we are using? What is the version? 0.223.3. It is a version. It is what? Executed while running this code. So that is the version which is available in my desktop. Right. Then what is it? The next block is what? We have seen superposition, entanglement, and teleportation. We will see about little bit about teleportation later. Then if you take any quantum computing program, the parts of quantum computing program contains quantum register, classical register, followed by quantum circuit, quantum gates and your quantum circuit. From the quantum circuit, we need to measure the output. So what is the building blocks? Quantum register should be passed your classical. Then there will be gates to perform various operations. And with the combination, it will generate a quantum circuit. From circuit only, we need to measure our output, right? So in that, we have the components what? Various gates available in quantum computing world. The first one is what? Pauli gates, represented by I, X, Y, and Z. And the Hadamard H. So this is one beautiful gate. Why I am saying beautiful gate, right? This gate is going to be purely, Hadamard is going to be purely quantum gate. What is that? We can apply Hadamard gate over only which? Over only quantum register or qubits. It is not possible to apply over classical component. So that is the reason what Hadamard is a purely quantum gate. Hadamard is what? Purely quantum. Next, phase gates. That is the reason we are talking about trigonometry and various things. Next, controlled phase gate, Cartesian rotation gates, controlled X gate, and the swap gates. So these are all various gates which is available in what? In any quantum computing, which is highlighted among the all, which is highlighted, Hadamard and what? Controlled. These gates are what? Important, frequently used and the most useful gates. Hadamard and the control NOT gate is what? C NOT gates are what? Mostly useful and what? Widely used gates in any quantum computing environment. Is that clear? Right. Next, block sphere. Next is what? Block sphere. Any idea what is block sphere? What it contains? Any guess? What is block sphere? By looking at the diagram, tell me what is block sphere. Put your answers in chat box.
Who do you want?
Yes.
Hello?
Yes.
Hello. Okay, so the block sphere is the quantum, represent the quantum gate that is between the 0 and the 1.
Right. So we are saying what? We are going to deal vectors. Each and every component present in quantum is what? Going to be vectors. And it is having how many coordinates? It is having more than 2 coordinates. So in order to handle these kind of situation, so what is the thing? We are depending upon this block sphere. And there is a arrow mark, right? It is a unit vector of radius 1 centimeter. What is that? So this is what? A sphere which contains 3 axes and is what? 1 by 1. It is having what? 1 unit centimeter of what? 1 by 1 centimeter. Right. That is what the thing. Then there is another thing about block sphere. So what is the use? The use of block sphere is going to be what? State of quantum bit as points on its surface. What is that? Shows the purpose of block sphere is what? State of quantum bit as points on its surface. So how can we process or we can rotate? Happens around x-axis, y and z of a unit radius 3D sphere. It looks like how? Unit radius of 3D sphere around x-axis, x, y and z. Here it is a point. It contains what? Contains angular coordinates and azimuthal coordinates. What is that? It contains angular coordinates and azimuthal, whereas clockwise coordinate and anti-clockwise coordinates. So that's about your angular coordinates and azimuthal. Modeled using Hilbert space. How it is modeled? The block sphere is what modeled using a Hilbert space. It's a mathematical representation of the block sphere. Right? Let's move further. Right. So what are the operations we can perform over our quantum gate with respect to state transformation? First is what? Over x, 180-degree rotation around the x-axis on block sphere. Then if we call y, it is what? 180-degree rotation around the y-axis on block sphere. Then if it is z, if you call, then what is happening? 180-degree rotation around the z-axis on the block sphere. It is block sphere. Then what happens? Hadamard gate. If we call Hadamard gate, then what is happening? We are able to get equal superposition. Generally, quantum particle is in superposition. Then what is the beauty? If we apply Hadamard gate, then what is possible? We can able to achieve equally superposition. X is plotted to Z, and Z is what? Plotted to X. So in this we are able to get what? Superposition. Then it is what? I stands for identity gate. And whereas this is what? Single gates. These are all what? The first three are going to be single gate. And it is what? Identity gate is also going to be single. The next one is what? C0. It stands for controlled NOT gate. So controlled NOT gate is what? Control NOT gate is for more than a bit. It is for 2 qubits. Control NOT gate is for which operation? Performing over 2 qubits. Does not change the control of the qubit. What that does? It does not change the control of the qubit. In which direction it is going to impact. Next, Toffoli controlled C0 gate. So these are all the various gates. Right. So Brian is showing something, right? So what is that? After registers and doing all the combinations, then what is that? Gates. Then it combines to form what? It combines to form quantum circuit. What is that? Gate along with register is able to form what? So what is this? Is our qubit. What is this? Classical register to measure our what? This symbol is what? This symbol is for NOT. A single qubit along with NOT, and we are measuring the output. What is there in the output? So whatever it is in the output, we can able to see from where? C0 gate. We are getting from where? C0. Next, 2 qubits. Now we are having what? Q0 and Q1. Then what is that? I am applying 1 NOT in the first qubit, 0th qubit, and 1 NOT in the first qubit. Then we are measuring the measuring the output from, then measuring the output from where? Output from the circuit. Then we are what? This entire thing is what? This entire thing is going to be circuit. Quantum circuit is an entity responsible for measuring the output of any operation. Output of any operation. Continued. So what is this? This is original circuit. The second one is transpiler circuit. Once if you run any code on real-time quantum computer, then we can get what? we can get a equivalent circuit of original as transpiler circuit. This is only possible what? After running the code from where? After running the code from quantum hardware. When it is possible? Only running from the quantum computer. Right, next. 2 qubits. This is original circuit and this is one is what? The transpiled circuit of the original circuit of 2 qubits. Original circuit and what? Transpiled circuit of original circuit. Next, this is what? 4 qubits. What is that? In order to show you, I was prepared what? 4 qubits. Count how many number of bits are there? 1, 2, 3, and 4. So I have applied Hadamard with the first 0 bit, and what? I have combined first bit with 0 bit with the first one by applying C0, and I am measuring the output from C0. Next, in third qubit, I have applied Hadamard. Then I am applying what? Applying the C0 second bit with third bit. So I am applying the measurement function to classical register 2. From here we are getting the output of 4 qubits. Getting the output of what? 4 qubits. Right. Transpiler circuit. So next, so this is all about what? A general and what? A generalized Qiskit construction. Right. So what we can do with what? Qiskit. So we can do high level applications, core capabilities, and low level applications. As I said, Qiskit nature, Qiskit finance, Qiskit optimization, Qiskit machine learning. This is mainly focused on what? Qiskit nature, finance, optimization, and machine learning. Relating to simulating quantum mechanical systems, applications relating to optimization problems, application related to machine learning, and relating to financial modeling. This is general software development kit architecture of quantum information science toolkit. Qiskit Terra. So Qiskit team generally you can divide research team, development team, and learning team. Research, development, learning. So far they have what? 1,400 plus research papers generating through Qiskit from 2017. So Qiskit metal is designing what? Various processors. Qiskit metal is for what? Generate various processor, designing various quantum. So this is a quantum roadmap so far from 2019. 2019 run quantum circuits on the IBM cloud. 2020 demonstrated a prototype quantum algorithm applications. In 2021 run quantum programs 100 times using faster with using Qiskit runtime. Bring dynamic circuits to Qiskit runtime to unlock more computation. So we are in 2023. So what is happening in 2024? Improve accuracy. In 25, scalable quantum applications. Beyond 2026, they are going to increase the accuracy of quantum computing. Right? Qiskit application and modules. As it's same, this is the architecture, it is going to be followed. So this is all about, and already Brian have showed, right? Brian Inghamson showed you textbook. So right, this is what, so far what has happened? Quantum challenges. See, the purpose of quantum challenge is what? To generate and have a community learning. For that purpose, IBM quantum challenges are designed. 2019, 20, 21, 22. So what? I think day after tomorrow, the spring challenge of IBM going to start. From May 17th, spring quantum challenge is going to start. These are all the summer, and there is a program called the summer school. For a month, they are going to cover the various aspects of quantum computing, specifically focused on quantum machine learning. Then Qiskit Advocate program. So this is the other program offered by IBM. So this is a summary. So then quantum carriers. So carrier in India, carrier international, carrier roles in quantum, specifically in IBM, Qiskit tool and opportunities. Right. So this slide I will share you guys, and let me go to the important thing. From where you can learn quantum computing, right? The first and foremost, the beginner or introductory level book, right? Quantum Computing for Quantum Curious, authored by Ciaran Hughes, Joshua Isaacson, Anastasia Perry, Randall Fu, Jessica Turner. It is an open source book. Anybody can download. So this is the first book anybody can approach towards quantum computing. Right. Then there is a very famous book. It covers solutions as well as applications. Quantum computing solutions, solving real world problems using QC algorithm, authored by Bhagavan Kumari. Then Programming the Quantum Computers by Eric Johnson, Nick Harrigan, Mercedes and Jimeno Segovia. This is hard copy and book materials. Here it is the what? The main part. So this is what? If you wanted to learn, no sir, I wanted to switch my career from normal to quantum, right? From here you can learn. MIT offers you what? MIT offers you a quantum computing course, and they charge $1,500. How much they are charging? $1,500. And this is one famous course from India, offered by QPIA. It is from a famous academic institution, IISc, Indian Institute of Science. They are also approximately charging $750. So this is a place where you can learn course, online course for quantum computing. Then, in order to keep yourselves updated, so these are all the places where you can get what? Updated information about quantum computing. So IBM research blog, researchibm.com, quantum computing and their work. And Microsoft is also having their blog, cloud blogs, Microsoft / quantum. And the Waterloo Institute is having what? A place where you can get all the updates from this through their Institute for Quantum Computing. Then ACM, Accounting Computer Mystery, FIGARCH. So here you can get through ACM, you can get all the updates of quantum computing. Then there is a last blog, QUBIT report. So this is what. So in this link you can find what? Quantum Computing and Quantum Computing Research Institute. Worldwide we are having 36 institutes. They provide courses and research activity in quantum computing. So this is the link where you can find what? Quantum computing related and quantum computing research institute related information. Right. That's all about. Last but not least, I made all this presentation with help of my team members, Dr. V. Jayakumar, Assistant Professor, President University, and Lokesh from my university, Sakti J. Mahendra from my university, Parvata Kumaran from my university. That's all about theoretical presentation. I think Brian has shown you some exercise, right? So I am also planning to show you one or two things from Qiskit, right? How is it? So you should make a note of this one. In order to begin, you should have this knowledge, then it is going to be very helpful. Quantum computing prerequisite is maths required and your matrix and tensors, right? These slides are going to be what? Highlighted feature of what? Baby step towards your quantum computing and Qiskit. Let me stop sharing. Okay, any doubts so far theoretically?
Yeah, hello, Prakash. Thank you so much for your presentation. It was very interactive as well, and we appreciate it so much.
Actually, my interest is that I wanted to make you people very much close to quantum. In which are all the possible ways you are getting close to QC. So that I have shaped up. So definitely right. From this lecture, you guys will be able to closer to quantum learning resources and the quantum.
Thank you so much. So all that Prakash did was to incite us to quantum computing. And he did talk about what quantum computing is, the basics you need. So you heard him talking about superposition, entanglement, and all that. Those were the basics, the build-up, the blocks you needed. And the good thing as well, it's the concluding part, where he did make mention of resources, materials, sites you could visit, and all that. We will share Prakash notes with you. Prakash, I hope you don't mind we share your notes with them.
It is there. It is already there in the folder.
All right. So we will share your materials with them. Thank you so much. Please, any questions for Prakash?
I have one more thing. Let me show you.
You should have a question, please.
Yeah. Yes, yes.
Yeah, so they say you answered all the questions through your presentation, but maybe you want to hear from the other room. Any question, please?
Yeah, questions or else they can put it in chat box. They can ask questions or else they can put it in chat box.
Okay, so Prakash, there are a few questions for you. So we take the question, please.
Yeah,
Hello.
yeah. Hi.
All right. So my name is Caleb. This is my question. I want to ask, do we have more gates than what you showed to us? Like the more gates in quantum, like you spoke about the Hadama, spoke about the poly gates, spoke about the phase gates, spoke about the control phase gate. We have more gates in quantum computing. Then secondly, you want to know at least can give us the current research in quantum computing right now.
Okay. Yes, yes. You have two questions. The one is about the gates and about the research. I have the answer for you, right? See, in order to make it short, I have given only the gates. Yes. If you go in detail, we have so many. There is something, yes. So among them all, right, we need Hadamard and we need CNOT, right? Hadamard only makes your qubit equally superposition. So I wanted to convey that. So I have given focus on Hadamard, and CNOT is what? With the help of CNOT only we are going to construct entanglement. So these two are very, very layman simple gates. So that is the way I was given focus on these two. Yes, we have many. Yes, we have many. In Qiskit textbook, you can take a look about, but I have grouped with respect to their functionality. Okay, and your second question is what? Recent research, right? See, I am also like you guys, but I have one or two steps I'm ahead of you. Okay, so recently I am working with machine learning only. They are doing quantum machine learning, and we are doing what? So in the quantum machine learning, you can focus on classification or prediction. Healthcare, you can go for healthcare prediction, or else you can go for what? You can go for defense applications, for communications, etc. So it's from my side suggestion. Okay, I'm not saying it is overall. So with my experience, with my own experience, we are working with healthcare applications using quantum QGAN and all, and in another way we are using various quantum circuits to investigate deep reinforcement learning for some healthcare applications, gentlemen.
Thank you. Thank you, Prakash, for your response. Please, any more questions?
Yeah.
I don't know if from Prakash's presentation, he made available to us very important resources you could get engaged with, like the IBM challenges. And I think one is coming on soon, maybe, I think this month or so, the spring challenge. I mean, you can give it a shot. Maybe I'll look for the link and share with you on the page. You can look at that. He did mention of Qiskit advocates. I think Brian also mentioned that as well. So please, kindly
Yes.
visit all those important sites.
Yeah,
And you can follow Prakash on LinkedIn. He will be a great guide to you as well.
Yeah. So you want me to elaborate a little bit about advocate and what advocate and certification developer, right?
No, I was just telling them you did mention it, so they can look it up.
So my LinkedIn.
Yes.
Yes. So since you type my name exactly like Satyaprakash Palniappan, they will get, or else I will provide my LinkedIn. I will provide you my LinkedIn profile. Is that fine?
Yeah.
Yeah. Let me provide my LinkedIn profile.
Okay.
Yeah. Any other questions? See, from where start, right? If you are beginner to quantum, right, don't hesitate. First you start read like storybooks. Storybooks are for quantum computing books. So in the beginning it will be tough. I know. So you go through day by day, right? Once you again go back and go through and go back and go back, right? Then things from the book will be familiarizing with you. The first and foremost book is what? QC for QC, Quantum Computing for Quantum Curious. It's a very nice book and a very, very important book in quantum learning. Nielsen book is very tough for beginners. Okay. Chang Nielsen, right? It is very elaborated, but it is not suggested for beginners.
Thank you so much, Prakash. It was great having you. We look forward to seeing more of you in future workshops and activities.
Yeah, I have given you my LinkedIn profile link.
All right, thank you. So we share his LinkedIn link with you so that you can follow him.
Yes. And okay, that is regarding book and online course. If you have financial freedom, you can go for MIT X Pro. That is my suggestion.
All right.
It's costly. I completely agree. It is approximately 1,500 USD. But their setup and process is very, very clear and neat.
Thank you so much, Prakash.
Mm-hmm.
We appreciate you so much. Thanks for, coming around as well. We look forward to see you in future, in person, maybe in our next workshop, in-person workshop. You will come to Ghana to do the presentation. Thank you.
Yeah. You know, I'm always what I respect African people. I have so many African friends here. I respect Africans for their kindness and their love towards any human being.
That's great. All right, thank you so much. I think all too soon we are ending day one. It's been wonderful. It might look tiring a little. That's why it's quantum computing. I heard you heard Brian. You don't get everything at a go, but gradually as you build on the basics, you get to somewhere. No one is perfect yet. We are all still learning. So we are encouraging you. Just go back, go through what you have learned, build your network, just, entangle among yourselves and learn from each other, which is the best way to go about doing computing Those who are coding, the programmers here, you know that you can't debug everything on your own. You need a hand to help you with debugging. It was nice having you around. We'll continue having day one on the page, sharing resource materials with you. And we ask for your feedback as well for day one. So kindly give us feedback on the page. Time is far gone. Some of us are going very far away, so we will kindly ask that your feedback, just put it on the platform for us, and we'll continue working on it to get better for day two and future workshops as well. Any other concern before we end the day? Okay, so we are asking for feedback. So just on the screen, the URL there, just type attendance for today. You enter your name, give us a short feedback before you sign off. We'd like to thank the organizers, our sponsors, and most importantly, our participants. Without you, this workshop wouldn't have come up. So we are grateful to you and for your presence as well. And to our speakers today, Brian and Prakash, we are grateful to them as well. Thank you so much. Please, day two continues tomorrow. It's going to be interesting.